From the Stone Age to the age of the Industrial Revolution and beyond, machines have improved human comfort, allowed us to exceed our capabilities as a species, and freed up our time that used to be spent on mundane tasks. Even today, we spend a significant number of hours every day doing chores, be it driving or cooking or cleaning, tasks that can be delegated to a robot to increase efficiency and free up time for humans. The artificial intelligence revolution of the 21st century is the latest and most disrupting wave to upheave our design of machinery. The self-driving car market alone is valued at 7 trillion USD. Similarly, manufacturing automation is one of the earliest areas of application of robotics that has been leading other industries in terms of speed of adoption and development. Already, nearly 60% of manufacturers are using some kind of robotics technology to make the manufacturing process more efficient. Robotics is also disrupting biology through the automation of biology labs. A lot of biology today is repetitive tasks that are still done manually, but robotics can automate a lot of these mundane tasks, allowing scientists more efficiency in their work and the ability to quickly prototype, test experiments within R&D, or even manufacture drugs at a massive scale. The top challenge for further adoption in robotics used to be the cost in robotics. However, the cost of robotics production is decreasing rapidly. Over the past 30 years, the average robot price has fallen by half in real terms, and even further if you compare this relative to labor costs. This trend is leading in robotics and allowing it to be more widely adopted in demand for various applications all around the world. The advent of deep learning and compute explosion, especially through GPUs and TPUs and edge computing, have had far-ranging disruptive effects on how we can actually approach robotics. The best vision and natural language algorithms in the world are now purely machine learning based. Similarly, control engineering is now being disrupted in multiple ways due to the advancements in AI. This transforms robotics from a problem that attempts to solve specific use cases within constrained environments using classical algorithms to a very generic manifestation of a physical intelligence trained on a huge amounts of data and powerful and accessible compute. Challenges have also shifted to solving the data problem using learning methods such as reinforcement learning, imitation learning for teaching robots tasks, and using simulation and sim-to-real methods to be able to do generalized tasks today within robotics. Today, I'll be diving deeper into how we can build models that are computationally efficient, especially when handling a large amount of real-world robot data or even simulation data. Alongside this, I'll be touching upon vision-based imitation learning systems that aim to solve the problem of generalization in robotics. Before I dive into this, I wanted to briefly touch upon some of my research within these areas. Previously, I worked as a machine learning developer at Hanson Robotics under PhD David Hanson, where I developed neurosymbolic AI and a closed-loop vision approach for improving the manipulation of Sophia the robot. Sophia the robot is one of the world's most advanced human-like robots who can make multiple facial expressions, understand sentences, and have casual conversations with humans. My work with neurosymbolic AI and vision approaches was integrated into the Sophia 2020 platform, which is a framework for human-like embodied cognition that will advance Sophia's expression, manipulation, perception, and design. We are currently also working to publish an updated paper on our low-cost robotic hand and open sourcing the hand design and control that we develop for people to further develop and build on top of. To further apply my work in machine learning, robotics to rehabilitation tech, I dived deeper into prosthetics and found an extremely pressing problem. Prosthetic arms today can cost anywhere from $10,000 to $100,000 or more for an advanced myoelectric arm. Due to the high cost, over 150 million amputees globally are left without a prosthetic. Alongside the cost, patients usually have to undergo physical therapy for over 3 months to understand how to utilize the prosthetic due to poor grasping and difficulty in using them. To lower the cost of prosthetics and make them easier to use, I led a team at the Blink Lab, and working with Professor Dr. Braz at San Jose State University, I developed a vision-based control framework using a generative grasping convolutional neural network to improve manipulation and learn grasping for a prosthetic hand. This was implemented with a depth camera that was mounted onto the wrist and on top of the actual prosthetic, which captured depth images containing the object that the amputee wanted to grasp. The algorithm goes pixel by pixel in the image that it captures, and then it calculates the best grasp in the image to then execute on this via a command sent to the prosthetic controller. We also developed a new 3D printed material and design that is able to reduce the cost of these prosthetics from $10,000 on average to just $700, making the arms much more accessible to amputees globally. This work does not just apply to prosthetics, but also other wide-ranging rehabilitation devices and assistive technologies such as hand exoskeletons that are used for recovering motor function of the hand for stroke patients. The majority of people with neurological conditions such as stroke and spinal cord injury suffer from loss of motor function in either one or both of their hands. Currently, exoskeletons are used to help them recover motor function through repetitive hand motions, but a lot of these existing exoskeletons are really bulky, expensive, and difficult to use. So you often have to go in physically into a lab and need to have someone there supervising you in order to actually use a lot of these devices. So I worked with the Harvard Biodesign Lab to leverage their soft robotic toolkit to build a low cost and also a portable glove, a glove that people can utilize at home or anywhere, just using soft robotics and machine learning for helping these stroke patients with neuromuscular rehabilitation. And essentially this helps patients improve their dexterity and also help them restore function. At the moment, I'm working with NVIDIA and the Vector Institute on ML research, and happy to chat more about that if any of you are interested to learn more. Now, when it comes to using AI in robotics, one of the things that have come to light over the past few years is the increasing need for compute within AI. OpenAI actually showed over the past few years that there's been a significant increase in the amount of compute that is required to perform deep learning applications and to do the training for deep learning. Since 2012, the amount of compute used in the largest AI training runs has been increasing exponentially with a 3.4-month doubling time, which, just for context and by comparison, Moore's Law has a 2-year doubling period. So it's definitely grown by over 300,000 times in terms of the amount of compute that we need to drive and increase the accuracy of a lot of the tasks that we're trying to achieve within robotics. Another important area where we want to do compute is actually moving the compute from the cloud to the edge itself. And this is a really emerging trend within robotics that you'll see. Because the power needed for certain model is actually dominated by moving the data itself. So it's not the computations themselves that are expensive, but moving the data to the computation engine that's expensive. There are a couple of reasons for why using edge computing can be really beneficial. One of these reasons has to do with communication. So in a lot of places around the world, you might not have a very strong communication infrastructure. So you don't want to necessarily have to rely on a communication network in order to do a lot of these applications. Removing your tethering from the cloud is really important for this. Another area is within privacy. So if you think about a lot of applications, they might have data that's really sensitive, especially within healthcare. So it's much more secure to bring the compute to the data itself through edge computing rather than sending the data to the cloud. The last reason has to do a lot with latency. So one of the other compelling reasons is that latency. So if you specifically think about an application such as autonomous navigation robotics or self-driving vehicles, which are a lot larger applications of robotics, you need to interact with the real world. So if you're driving on a road and your car detects, let's say, an obstacle, the car might not have enough time to actually send that data to the cloud, wait for it to be processed, and then send those instructions back in. So the car needs to be able to act quickly, obviously within this given situation. One of the big challenges of doing processing in the robot or in the device itself actually has to do with the power consumption that these devices take up. So for example, a self-driving car has been reported to consume over 2,000 watts of power just for the computation itself, which is just used to process sensor data that it's actually collecting. So this actually generates a lot of heat, takes up a lot of space, and often also needs water cooling. And you can see an example of what this looks like on the left side here. And you can also imagine that this is going to be much more challenging if you actually shrink down the form factor from this large car to, let's say, like a smartphone, which is much smaller. And so these smaller robots have very limited energy capacity since the battery itself is limited based on the size or the weight of the device, for example. And then another big reason is if you actually take a look at the embedded platforms that are currently used for embedded processing for these particular applications, they tend to consume over 10 watts, which is in an order of magnitude higher than the power consumption that you typically would allow for these handheld devices. So in the past decades, what we would usually do to address this challenge is that we'd wait for transistors to become smaller, faster, and more efficient. However, this has become a huge challenge over the past few years since transistors are not getting more efficient. So for example, Moore's Law, which typically makes transistors smaller and faster, has actually been slowing down. And Dennard scaling, which has made transistors more efficient, has also slowed down or ended. So you can see here over the past 10 years, this trend has significantly slowed down or flattened. We need to turn towards specialized hardware to achieve the significant speed and energy throughputs that we actually require within robotics. When we talk about designing specialized hardware, this is really about thinking through how we can redesign the hardware from the ground up for the AI and robotics tasks that we'd like to do. If you look at a popular example and application within autonomous navigation, the real challenge here is that these applications use a lot of data. So for example, one of the things you need to do in autonomous navigation is what we call semantic understanding. So you need to be able to identify which pixels belong to what. So on this example here on the left, you can see that in the scene, a certain pixel will represent the ground, a certain one will represent the sky, and another pixel will represent the actual person. And so you want to be able to go pixel by pixel and actually classify what category it fits into. And this is an important type of processing. Often if you're traveling very quickly, you want to be able to do this at a very high frame rate. You might need to have a large resolution, which usually results in a high amount of pixels or data that you need to process. There's also geometric understanding, which is when you're navigating, you want to build a 3D map of the world that's around you. The longer you travel, the greater the map and the data that you collect will be. One other important thing that you need to do is actually depth estimation. So if you're given an image, can you essentially estimate how far a given pixel is from a person or a certain object? Another important area is within semantic segmentation. So this is useful to understand your environment. However, a lot of existing deep neural networks, such as convolutional neural networks, commonly use an image data that are commonly used for any sort of image task, image classification, segmentation, as we mentioned, usually use hundreds of millions of operations and weights to actually compute. So obviously this becomes a huge problem when it comes to computation and being able to run these models efficiently and quickly. Now, there's a few things that we can do to leverage things that we can leverage to be able to actually overcome these problems. So one of these things is what we call data reuse opportunities. If we read the data once, we can actually reuse it multiple times for many operations. The first example of this is what we call convolutional reuse. So we're taking a filter and we're essentially sliding it across the input image. So that's kind of at a high level what a convolutional operation does. And so as a result, the activations from the feature map and the weights from the filters are going to be reused in different combinations to compute the different max itself. Another example is that we're going to apply multiple filters on the same input feature map. So that means that each activation in that input feature map can be reused multiple times across the different filters. Finally, if we're going to process many images at the same time or many feature maps, a given weight in the filter itself can be reused multiple times across these input feature maps. So this is what we call a filter reuse. So there's a lot of these great opportunities for filter reusing that we actually have within the neural network itself. What we can do to actually exploit these reuse opportunities is build a memory hierarchy that contains very low cost memory that allows us to reduce the overall cost of moving this data. If I build a multiply and accumulate engine, I'm going to have a very small memory engine right beside the multiply and accumulate engine. And by small, I mean something on the order of under a kilobyte of memory locally beside that multiplying accumulated engine. This is helpful because accessing that very small memory can be very cheap. Ideally, we would like to access all the data from this very small local memory, but the challenge here is that it's very small, right? It only contains 1 kilobyte of data, but we're talking about neural networks here that are millions of weights in terms of their size. So the question is, how can I break up a large piece of work into smaller chunks so that I can access them all from this small memory itself? One approach to do this is what we call weight stationary. And the idea here is that I'm going to store the weight information of the neural network in the small local memory. And as a result, you really minimize the weight energy. But the challenge here is that the other types of data, such as your input activation, which is shown in blue here, or then the partial sums, which are shown in red here, they still have to move through the rest of the system itself, through the network and from the global buffer. So typical types of work that are actually popular that use this kind of data flow or weight stationary data flow is what we call it, because the weights in this scenario remain stationary, are things like the TPU from Google and the NVIDIA NVDL-A accelerator from NVIDIA. What's important to think about is that maybe you want to reduce the data movement of all different data types, right? So not just the weights, but being able to control and move and control all the types of energy and the data types. A way to do this is through the row stationary data flow. Within each of the processing elements, you're going to do one row of convolutional. And this row is a mixture of all the different data types, such as the weights of the filter, you have the activations of your input feature map, and then you also have your partial sum information. So you're really trying to balance the data movement of all different data types, not just one particular data type. Now, this screen here basically shows examples of how you can expand a 1D convolution into just higher dimensions, into like a 2D convolutional, and then there's also just higher dimensionality that can map onto this architecture as well. So using these methods can make training vision-based neural networks much more computationally efficient. Now that we understand the compute part of this network, I'll be diving deeper into a paper by Google, Berkeley, and Stanford, which demonstrates a vision-based robotic manipulation system that was utilized to generalize and do novel tasks. So they approached the challenge by developing an interactive and flexible imitation learning system that could learn from both demonstrations and interventions and can be conditioned on different forms of information that convey the task, including pre-trained embeddings of natural language or videos of humans performing the actual task. They tested the model on roughly 100 distinct tasks and found that their system can perform 24 unseen manipulation tasks with an average success rate of 44%. This is without any robot demonstrations for those tasks. They also collect a large-scale data set of around 26,000 episodes of 100 diverse manipulation tasks and train a 7-degree of freedom multitask policy that conditions on task language strings or human video. They show that the system produces a policy that is capable of generalizing zero shot, so essentially to new unseen tasks without having seen them before or having been trained on those tasks before. Now, there's a couple of benefits to using this approach, and they really developed this interactive imitation learning system with 2 key properties that enable for high quality data collection and also generalization to entirely new tasks. So first, the system incorporates shared autonomy into teleoperation to allow for the collection of both raw demonstration data and human interventions to correct the robot's current policy. Second, the system flexibility conditions the policy on different forms of task specification, including a language instruction or a video of a person performing the task. They focus on achieving zero shot, which is for language, and a few shot for video generalization to entirely new 7-degree of freedom manipulation tasks on a real robot, including scenarios without goal images and where task relevant objects are never really encountered before or seen within the training data itself. Now, the goal here is to train a conditional policy that can interpret RGB images together with a task command, which might correspond to either a language string or a video of a person. The policy is a mapping from images and the commands to actions, where the action space consists of the 6-degree of freedom pose of the end effector, as well as the 7th degree of freedom for continuous control of the parallel jaw gripper. The policy architecture is divided into an encoder, which processes the actual command into an embedding, and a control layer, which processes the coordinates of S and Z to produce the action A. This essentially means that this method incorporates auxiliary supervision, such as pre-trained language embeddings, which can help to structure the latent task space and facilitate generalization to tasks that were not seen during training. And this can include novel compositions of words and objects as well. So an RGB image from the head-mounted camera is passed through a ResNet 18 encoder. The policy network processes the camera image with a ResNet 18 torso, which branches from the last mean pool layer into multiple action heads. So each head is a multi-layer perceptron with 2 hidden layers of size 256 each, and then ReLU activations, and predicts each action modality. So this is the delta XYZ, the delta axis angle, and the gripper angle. FILM layers are then used and help influence the neural network computation via a simple feature-wise affine transformation based on conditioning the architecture on a task embedding, compounded from, computed either from the language or the video that is inputted into the model. The task conditioning is also linearly projected to a channel-wise scales, and what it does is it shifts for each channel of each of the 4 ResNet blocks that are in the architecture. So this model is really, really exciting because it shows some good results, especially early results for using a vision-based imitation learning system to be able to do generalized tasks in robotics. Now, robotics, both as science and practice, is really at the cusp of disruption from data-driven deep learning, a disruption that is driven by the widespread industrial deployment of huge neural nets and end-to-end learning of generalized robotics tasks, be it for self-driving, consumer robotics, or even industrial manufacturing. What I've touched on today is really just the peak and the start of what's happening in this field. And I'm personally really excited to see these advancements and what will happen in advancing and pushing forward computing data and model architectures within the next 5 to 10 years for us to really put these systems in regards to learning methods like RL and imitation learning into production so that we can start using these within companies and within industrial labs that exist today. Thank you so much.